Okay, so this is 8.2 example 1 where we deal with some actual transformations. And I think right off the bat, at least for this example, I'm going to rewrite it immediately. I'm going to write this as y equals log base 3 of x minus -9 plus 2. And the reason I do that is that allows us to identify that h is -9 and k is +2. So there's a horizontal translation 9 units left, not right, that's really important, and then there's a vertical translation of 2 units up. Now, what this allows me to do is talk about where these points would go, or my mapping, which is what I really enjoy doing, or I find it very helpful. X comma y on the untransformed graph will turn into x minus 9 comma y plus 2 on my new function. Now, in terms of, what is the original function, it would be the simplest version of that logarithmic function, which in this particular example is y equals log base 3 of x. And that would be transformed into y equals log base 3 of x plus 9 plus 2. Now, if you want a nice systematic way of how we compare these, whatever the base in your transformed function had to be the base in the original function as well. Now, certainly from this is more than enough to identify those points. But what I'm going to do to try to make this maybe as simple as possible is I am going to talk about the points on y equals log base 3 of x. When x is equal to, sorry, I messed up there. When y is equal to -1, x is equal to 1/3. When y is equal to 0, x is equal to 1. When y is equal to 1, x is 3. When y is equal to 2, x is 9. I'll do one more here. That 27 comma 3 will go on that curve as well. Now, the best way of generating those points is to switch y equals log base 3 of x into 3 to the power of y is equal to x. And then essentially I'm just putting, integer values of y in and seeing what x is going to be. Now, if we ran these points through the mapping, this first one is a little bit ugly because I do have to subtract 9 from 1/3. 9 can be written as 27/3. So this is the brutal one. It's going to be at -26/3, comma, -1 plus 2 gives me +1. 1 comma 0 is going to go to -8 comma 2. 3 comma 1 is going to turn into -6 comma 3. 9 comma 2 is going to turn into 0 comma 4. You have to love when this happens because that is my new Y-intercept. And then finally, 27 comma 3 is going to turn into 18 comma 5. Now, what that gives me is the ability to, at least draw these points and then really connect the dots, which is pretty useful. And I think that is probably the first thing that we should look at what's happening here. And I'm going to draw this out really specifically, that this black line that I'm drawing is y equals log base 3 of x. And I'm going to try to get it to draw the asymptote at x equals 0 as well. We'll see if that worked, if it all brought it together. Good. So that's my standard function. And I'll write underneath it, I'll write it in black here, that y is equal to log base 3 of x is what that looks like. Now, to try to allow us to compare these, I am just going to grab my mouse so I can copy that quickly. And what we're going to picture is what would happen if we took that graph and moved it 9 units to the left and 2 units up. And I'm just going to actually change the color of this as well. So the red is our transform function. So I'm going to overlay them. And then what we're going to do is we're going to picture our transformations. So I'm going to move this 9 units to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere around there. And then I'm going to move 2 units up. So 1, 2. Now, the reason I wanted to draw this out is it's really important that the only thing that shifts our asymptote is that horizontal translation. So my new asymptote is 9 units to the left. And if I subtract 9, I get that my new asymptote is at x is equal to -9. The point that we knew is that it went through 0 comma 4, but what I want to do for X-intercept and Y-intercept, I want to keep on pushing that concept that we can do that algebraically again and again and again and again. Now, before we go anywhere, we're going to answer 1 and 2, which are our asymptote and our domain and range. So I'm going to do that for my red function. And I'll just draw it again so we can see it all in red. Sorry about that. So this is what my function looks like, roughly. Then we have a vertical asymptote right there. So my vertical asymptote, it is a vertical line, so it's at x equals -9. The domain is that x must be greater than -9 and any real number that satisfies that. And then the range is y is an element to the real. Now, before we go anywhere, I want to show you algebraically how to find that domain. One of the concepts that we're going to talk about, and we already have in chapter 8, is that you cannot take the logarithm of a non-positive number. Now, really what that means is that the inside, the argument of the logarithm, in this case x plus 9, has to be greater than 0. Well, if I solve that inequality, I get that x must be greater than -9. That was or is the domain of this function. And that's a useful thing to remember because that you can always go back and solve for it that way. Okay, the only other piece that we're going to do here is our intercepts. I'm going to label those as X-Intercept. I'll just put beside it, that means that y is equal to 0. And Y-Intercept, we already know what this is, but I'd like to confirm it. Every Y-Intercept, x is equal to 0. All right, well, let's do the easy one first, which I think is setting x equal to 0. That would mean that y is equal to log base 3 of 0 plus 9 plus 2. So y is equal to log base 3 of 9 plus 2. This is where practice helps. Log base 3 of 9, and I'm going to write it like this. I'm going to use maybe t. This is saying that 3 to the power of the value of the logarithm is equal to the argument, which is 9. What exponent do I need to make t to make that work? Well, 3 squared is equal to 9, which means that log base 3 of 9 is 2. What I'm going to do to try to help you guys at least a little bit in this chapter is I have some log mad minutes. I think there's 50 a page or something. I'm going to upload those onto Google Classroom. That is really useful if you're struggling with evaluating some simpler logarithms without necessarily grabbing your calculator each and every time. Now, to solve this, this means that log base 3 of 9 is 2. So I get that y is equal to 4 when x is equal to 0. So 0, 4 is my y-intercept. And we got lucky and kind of found that via transformations, but that's not always going to happen. The other side of this, the other half of it, is the x-intercept. If y is equal to 0, we have that 0 is equal to log base 3 of x plus 9 plus 2. A little bit harder to solve. I'm going to move the 2 to the other side to isolate my logarithm. I get that -2 is equal to log base 3 of x plus 9. And what I'm going to do now is I'm going to switch to exponential form to get rid of the logarithm. And that means that the base to the power of the value is equal to the argument. 3 to the -2 is 1 over 9. That's equal to x plus 9. I'm going to subtract 9 from both of those. And I get that my x-intercept occurs at 1/9 minus 9. Please don't leave your answer like that. That's a cop-out. We need to make sure you understand how to do this algebraically. What I would do to solve this is change that 9 into a fraction with the denominator of 9, and that looks like 81 over 9. Well, 1 minus 81 over 9 is -80 over 9. So my x-intercept is at -80 over 9, comma 0, because the y is always 0. Now, what we're going to do at this point, and it's a little bit tricky, is I'd like you to grab your calculator, because I'm going to show you how to type this in, even if you don't have base 3 on your calculator. All right, in order to do this on our calculator, we have to be comfortable with how to change the base. Let me move that up a little bit. So if we have y equals log base 3 of x plus 9 plus 2, the plus 2 is not inside the logarithm. So we're going to kind of leave it alone for now. What we're going to do is identify that log base 3 of x plus 9 can be written as log base 10 of x plus 9 divided by log base 10 of 3. And then after all that is done, we would be adding 2 to it. Now, the challenge is making sure we plug this correctly into our calculator. And where that challenge really lies is making sure that we're comfortable and confident with where we put our brackets. So on your calculator, we'll delete this stuff. We'll go back to our y equals. I am going to type in the log of, in a bracket, x plus 9. I'm going to close that bracket and then divide that logarithm by the log of 3. You must close the bracket after your logarithms. That is, in general, just a good habit to get into. And then finally, I would add the 2 on the outside. Now, I'm going to go to Zoom Standard. And I don't think it's going to look great, but it'll look good enough, I think. The problem, and the major problem with our calculator, is that it really does struggle with this near vertical line right there. It just does not graph vertical lines because they're not functions. So if we do want to find the y-intercept, it's the easy one. It's actually already there. But if I make x equal to 0, I get y equals 4. So that's reasonable. We knew what was on there. We could check a few different points if we wanted to. The problem with checking points is that your calculator is going to give you decimals. Now, I can cheat a little bit because we calculated the x-intercept. If I put -80 over 9 in for x, it tells me that y is equal to 0. But look what the calculator understands that as. -8.8888 repeating. Now, what I would also like to show you is look what happens when I try to put -9 in for x. Calculator just leaves it blank. That's because it doesn't exist at -9. But what about -8.99? or 3 nines, I guess. That does exist. And this is the weird part about the calculator. The line should be there, but the calculator doesn't draw it. So more than ever, I hope that this demonstrates that blind faith or blind trust in what your calculator is showing you is not really the preferred outcome in this course. We have to get to the point where we're comfortable with the transformations, comfortable with their base functions, that we know when our calculator is maybe not doing everything that it should or everything that a more advanced model could. All right, in order to find the X-intercept, if you wanted to do this algebraically, we would use second trace 0. I have to make sure my cursor is to the left of it. To the left of my X-intercept, the Y should be negative. To the right of my X-intercept, the Y should be positive, and then I'll guess. But it tells me this. Now, what you can do to get the actual value is quit out to the home screen and type in just X. When you hit enter, it'll take the value that you found off your graph, and then we can use our math frac to get that negative 80/9. This is not the preferred technique for solving this. You should be able to do this algebraically as well, but we'll practice more of that as we work through chapter 8.